Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The bright and dark features on surfaces. Across the solar system, the surfaces of planets, moons, and asteroids display remarkable contrasts between light and dark regions. These variations in brightness, called albedo features, paint cosmic bodies with patterns that range from subtle shadings to stark contrasts, each telling a story about composition, geology, and the forces that have shaped these worlds over billions of years. Consider Earth's moon, the most familiar example. Even without a telescope, you can see the dramatic difference between the bright highlands and the dark Maria, the ancient lava plains that early observers mistook for seas. The bright regions are ancient crust formed over 4 billion years ago when the moon was young, and its surface was still cooling from a molten state. This primordial crust is rich in a mineral called anorthosite, a type of rock that's relatively light in colour and highly reflective. These highlands are the original surface of the moon, battered by eons of meteorite impacts, but still retaining their pale character. The dark Maria formed later, between about 3.8 and 3.1 billion years ago, when massive asteroid impacts punched through the moon's crust and allowed molten rock from the interior to flood onto the surface. This lava was basaltic, similar to the lava that flows from volcanoes in Hawaii, and it's much darker than the highland material. The basalt contains more iron and magnesium than the ancient crust, and these elements absorb more light, giving the Maria their characteristic dark appearance. When this lava cooled and solidified, it created vast, smooth plains that still dominate the near side of the moon today. The moon's far side presents a different face, with far fewer dark Maria and much more bright highland terrain. This asymmetry puzzled scientists for decades. Why would one side of the moon have so much volcanic flooding, while the other side remained mostly ancient highland? The answer lies in the moon's structure. The crust on the far side is thicker, making it harder for lava to break through, even when massive impacts occurred. The near side's thinner crust allowed molten rock to more easily reach the surface, creating the face we see each night. Mars displays its own dramatic albedo patterns, visible even through small telescopes from Earth. The planet shows bright regions and dark regions that early astronomers mapped and named, imagining them to be continents and seas. The bright areas are primarily ancient highland regions covered with fine dust that's rich in iron oxide, essentially rust, giving Mars its characteristic red colour. This dust is incredibly fine, almost like talcum powder, and it reflects sunlight fairly efficiently despite its red hue. The dark regions on Mars are areas where the dust has been blown away by winds, exposing darker underlying rock or concentrations of dark sand. Some of these features change over time as seasonal winds redistribute dust across the planet's surface. During global dust storms, which can envelope the entire planet, the contrast between bright and dark features diminishes as everything gets covered in suspended dust. As the storm settles, the patterns gradually re-emerge, though sometimes in slightly different configurations than before. One of Mars's most prominent dark features is Syrtis Major, a broad shield volcano whose dark basaltic rock stands in stark contrast to the surrounding bright highlands. This feature was one of the first to be recognized on Mars and has been used for centuries to track the planet's rotation. The dark rock here is volcanic in origin, similar to the moon's Maria, and it resists being covered by the bright dust that blankets much of the planet. Mercury, the innermost planet, shows subtle but distinct albedo variations across its heavily cratered surface. The overall planet is fairly dark, reflecting only about 12% of the sunlight that hits it, making it one of the least reflective rocky bodies in the solar system. But within this generally dark surface, brighter and darker regions exist. Some craters have bright rays extending from them, where the impact that formed the crater excavated fresher material from beneath Mercury's space-weathered surface and scattered it across the surrounding landscape. The darker regions on Mercury include vast, smooth plains that, like the Moon's maria, formed when lava flooded the surface billions of years ago. But Mercury also has mysterious dark material that appears to have been deposited from volcanic eruptions in a more explosive fashion. This dark material, which may be rich in carbon or other volatile rich compounds, creates some of the darkest features on the planet's surface, appearing almost black in high-resolution images. Jupiter's moon Europa presents one of the most striking albedo contrasts in the solar system. The moon's surface is almost entirely water ice, but it's not uniformly bright. The cleanest ice is brilliantly white, reflecting nearly all the sunlight that touches it. But cutting across this bright surface are countless dark lines and streaks, forming patterns that remind observers of cracks in pack ice on Earth. These dark features are ridges and bands where the ice has fractured and material from beneath, perhaps salts, sulfur compounds, or organic molecules, has been exposed or deposited on the surface. Some of Europa's dark features appear reddish-brown, suggesting the presence of salts like magnesium sulfate or sodium chloride that have been altered by radiation from Jupiter's intense magnetic field. The radiation breaks apart molecules and creates new compounds, darkening and discoloring the surface materials over time. The brightest regions on Europa are thought to be the youngest, places where fresh ice has recently been exposed or deposited, while the darker, more discolored regions are older surfaces that have been exposed to radiation for longer periods. Saturn's moon Iapetus displays perhaps the most dramatic albedo contrast of any body in the solar system. One hemisphere is as bright as fresh snow, reflecting about 60% of incoming sunlight, while the other hemisphere is as dark as asphalt, reflecting only about 4%. The boundary between these regions is sharp and striking, creating an appearance that reminded astronomers of a yin-yang symbol. The dark material, concentrated primarily on the leading hemisphere, the side that faces forward as Iapetus orbits Saturn, may have originated from dark dust in Saturn's system that Iapetus swept up as it moved through space, or it may have erupted from the moon's interior through cryovolcanic processes. Once the initial dark material was deposited, a feedback process likely amplified the contrast. Dark surfaces absorb more sunlight and heat up more during the day. On Iapetus, where daytime temperatures can reach as high as -230 degrees Fahrenheit in sunny areas, this slight extra heating in the dark regions causes water ice to slowly sublimate, transition directly from solid to vapor. This water vapor migrates to colder regions, including the bright trailing hemisphere, where it refreezes. Over millions of years, this process has darkened the dark hemisphere further by removing its ice and brightened the bright hemisphere by depositing additional ice there. Pluto, visited by NASA's New Horizons spacecraft in 2015, revealed a surface of surprising complexity and dramatic albedo contrasts. The dwarf planet's most prominent dark feature, informally named Cthulhu Regio, is a vast region near the equator that appears deep red-brown in colour. This dark material is thought to be complex organic molecules called tholins, formed when ultraviolet light from the distant sun and cosmic rays interact with methane and nitrogen in Pluto's thin atmosphere. These molecules rain down onto the surface, accumulating over time and creating the dark coloration. Adjacent to this dark region lies Sputnik Planitia, a vast plain of bright nitrogen ice that forms the western lobe of Pluto's heart-shaped feature. This bright ice reflects much more light than the surrounding terrain. The contrast exists because nitrogen ice is relatively bright and because this region is geologically active. The ice is constantly churning in slow convection cells, bringing fresh material to the surface and preventing the accumulation of the dark organic compounds that colour other parts of Pluto. Asteroids show their own albedo variations, though measuring them requires careful observation. Some asteroids are quite dark, reflecting only 3 or 4% of the light that hits them. These are typically carbonaceous asteroids, rich in carbon compounds and hydrated minerals, making them among the darkest natural objects known. Other asteroids are much brighter, particularly those made primarily of metal or rocky silicates. The contrast between dark and bright asteroids tells scientists about their composition and helps trace them back to different regions of the early solar system where they formed. Even within a single asteroid, albedo features can exist. Some asteroids show bright spots that might be exposed fresh material where an impact has recently broken through a darkened, space-weathered surface layer. Others show variations that might indicate different minerals or rock types at the surface. The asteroid Vesta, one of the largest in the main belt, shows dramatic brightness variations across its surface, with some regions nearly twice as reflective as others. The process called space weathering affects the brightness of surfaces throughout the solar system. When cosmic rays, solar wind particles, and micrometeorites bombard a surface over time, they gradually darken it and change its reflective properties. Fresh surfaces, recently exposed by impacts or other processes, appear brighter. Ancient surfaces that have been exposed to space for billions of years generally appear darker and redder than they would if the same material were fresh. On the Moon, this space weathering creates the subtle variations in brightness visible within both the highlands and the Maria. The rays around young craters appear bright because the impact has excavated fresh material. Over hundreds of millions of years, these rays gradually fade as space weathering darkens the ejected material, causing it to blend in with the surrounding ancient terrain. Comets show extreme albedo contrasts as well. The nucleus of a comet, the solid body beneath the gas and dust, is among the darkest objects in the solar system, often reflecting only about 4% of incident light. This dark material is thought to be a mixture of organic compounds, similar to the tholins on Pluto, mixed with dust and ice. But when a comet approaches the Sun and begins to release gas and dust, it can develop bright areas where fresh ice is exposed and actively sublimating, creating jets of gas that appear much brighter than the surrounding dark nucleus. The study of albedo features requires careful measurement. Scientists use photometry to measure exactly how much light a surface reflects at different wavelengths. By comparing the brightness at different wavelengths, they can determine not just whether a surface is bright or dark overall, but what specific materials might be present. Iron-rich minerals absorb light differently than ice, which absorbs differently than sulfur compounds or organic materials. Each substance has its own spectral signature, revealed through its albedo characteristics. These patterns of light and dark across the surfaces of solar system bodies are not mere decoration. They are maps written in brightness, showing us where different materials exist, where geologic processes have been active, where impacts have occurred, and how surfaces age under the constant bombardment of radiation and particles from space. Every bright crater ray, every dark lava plain, every reddish streak of organic material tells part of the story of how these worlds formed and evolved, creating the complex and beautiful patterns we observe across the solar system. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival. In boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Barophil's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environments can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind: long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web. This mysterious substance, which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light years across, and stretching for hundreds of millions of light years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000 billion suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the Local Group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions a billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich, structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure. this intricate architecture that connects everything in the universe into one enormous, evolving pattern. The biosignatures that reveal living planets. Detecting life on distant planets represents one of the greatest challenges in astronomy. We cannot visit these worlds, cannot scoop up soil samples, cannot peer through microscopes at alien microbes. Most exoplanets appear as nothing more than tiny dips in their star's brightness as they transit, or slight wobbles in the star's position caused by the planet's gravitational pull. Yet from these minimal observations, measurements of light passing through a planet's atmosphere during transit, analysis of the planet's reflected light, characterization of its temperature and size, astronomers hope to determine whether life exists on worlds many light years away. The key lies in biosignatures, detectable signs that life is present, chemical or physical features that cannot easily be explained by non-biological processes, and that point toward the presence of living organisms modifying their planet's environment in measurable ways. Oxygen stands as the most famous biosignature, the gas that astronomers most eagerly search for in exoplanet atmospheres. On Earth, oxygen makes up 21% of the atmosphere, a concentration vastly higher than would exist without life. Oxygen is highly reactive. It combines readily with rocks, organic molecules, and other materials, removing oxygen from the atmosphere unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria use sunlight to split water molecules, releasing oxygen as a waste product. Without this biological production, Earth's atmospheric oxygen would disappear within a few million years as it reacted with surface materials. Detecting oxygen in an exoplanet's atmosphere would strongly suggest the presence of photosynthetic life, though not definitively. Oxygen can be produced through non-biological processes. Photodissociation of water vapor by ultraviolet light, for instance, can split water molecules and release oxygen. But these abiotic processes typically produce only small amounts of oxygen compared to the abundant oxygen that photosynthesis generates. A planet with significant oxygen in its atmosphere, particularly if that oxygen persists over long periods, would be a compelling candidate for hosting life. However, oxygen alone doesn't guarantee life, and the absence of oxygen doesn't rule out life. Earth's atmosphere contained very little free oxygen for the first 2 billion years or more of life's existence. Early life consisted entirely of anaerobic organisms that didn't produce oxygen. Even after photosynthesis evolved, it took hundreds of millions of years for oxygen to accumulate in the atmosphere, because the gas initially reacted with dissolved iron in the oceans and with rocks before building up in the air. An alien planet might be teeming with life, yet have no oxygen signature if that life hasn't evolved oxygenic photosynthesis, or if oxygen-producing organisms haven't yet generated enough oxygen to overwhelm the chemical sinks that remove it. Methane represents another important biosignature, particularly in combination with oxygen. Methane and oxygen react with each other readily. In the presence of oxygen, methane breaks down relatively quickly through oxidation. For both gases to coexist in significant quantities in an atmosphere, something must be continually producing them faster than they react and disappear. On Earth, biological processes produce both gases. Photosynthesis produces oxygen, while certain bacteria called methanogens produce methane as a metabolic waste product. The simultaneous presence of both gases in substantial concentrations would be difficult to explain through non-biological chemistry alone. Methane itself can be produced abiotically through geological processes. Volcanic activity, hydrothermal systems, and reactions between water and certain rocks can all generate methane without life. But these sources typically produce methane at lower, steadier rates than biological sources. If observations show variable methane levels, perhaps seasonal variations suggesting biological activity that waxes and wanes with seasons, or if methane concentrations are higher than geological sources could explain, this would strengthen the case for biology. Phosphine burst into the biosignature conversation in 2020 when scientists reported detecting this gas in Venus's atmosphere. Phosphine consists of one phosphorus atom bonded to 3 hydrogen atoms, and on Earth it's primarily produced by anaerobic bacteria living in oxygen-free environments. Phosphine is quickly destroyed by ultraviolet light and chemical reactions, so detecting it in an atmosphere suggests something must be continuously producing it. The Venus detection remains controversial. Subsequent observations haven't definitively confirmed the phosphine signal, and some scientists argue that non-biological chemistry could produce phosphine in Venus's harsh environment. But the episode highlighted phosphine as a potential biosignature worth searching for, particularly on worlds very different from Earth. Ozone, a molecule consisting of 3 oxygen atoms, serves as a secondary oxygen biosignature. Ozone forms in atmospheres when ultraviolet light breaks apart molecular oxygen, and the freed oxygen atoms recombine into ozone molecules. Ozone is easier to detect spectroscopically than molecular oxygen, so finding ozone in an exoplanet's atmosphere provides strong evidence that molecular oxygen is also present, which in turn suggests photosynthetic life. Ozone also absorbs harmful ultraviolet radiation, protecting planetary surfaces from DNA-damaging rays. The presence of an ozone layer suggests not only that photosynthetic life produces oxygen, but also that conditions at the surface might be suitable for more complex life that would otherwise be sterilized by ultraviolet radiation. Nitrous oxide, laughing gas, represents another possible biosignature. On Earth, certain bacteria produce nitrous oxide as a byproduct of nitrogen metabolism. Like oxygen and methane, nitrous oxide is reactive and doesn't persist indefinitely in atmospheres without continuous production. Detecting significant amounts of nitrous oxide, particularly in combination with other biosignature gases, would strengthen the case for biological activity. However, nitrous oxide can also be produced abiotically through lightning, volcanic activity, and chemical reactions in the atmosphere, so its detection alone wouldn't be definitive. Sulfur compounds offer additional biosignature possibilities. Dimethyl sulfide, produced by marine phytoplankton on Earth, has a distinctive spectral signature. Hydrogen sulfide, while toxic to most Earth life, is produced by certain bacteria and might be an important gas in alien biospheres based on sulfur chemistry rather than oxygen. Carbonyl sulfide, though produced both biologically and geologically, might still serve as a biosignature when detected in combination with other gases in ways that geological processes can't easily explain. The key to biosignature detection often lies not in finding a single gas, but in detecting combinations of gases that shouldn't coexist in equilibrium. Chemical disequilibrium, the simultaneous presence of gases that react with each other, suggests that something is continually producing those gases, driving the atmosphere away from chemical equilibrium. Life is inherently a disequilibrium phenomenon. Living organisms take in certain chemicals and energy, use them to maintain organization, and grow and excrete different chemicals as waste. This metabolism creates chemical imbalances that wouldn't exist in a sterile abiotic system at equilibrium. Earth's atmosphere is far from chemical equilibrium precisely because life constantly produces gases that react with each other and with the environment. An alien planet with life would similarly maintain chemical disequilibrium, though the specific gases involved might differ completely from Earth. The challenge lies in distinguishing biological disequilibrium from geological or atmospheric processes that can also create unusual gas combinations. Temporal variations in biosignatures provide additional evidence. Seasonal changes in atmospheric composition might reflect biological cycles. plant growth during spring and summer, dormancy during fall and winter. Daily variations might reflect photosynthesis, starting at dawn and stopping at night. Finding these rhythmic patterns would be strong evidence for biology, because non-biological processes rarely produce such regular, predictable cycles tied to light and seasons. Surface features offer another category of biosignatures. On Earth, large-scale biological activity affects the planet's appearance in ways that might be detectable from space. Vegetation reflects light in characteristic ways. The red edge, where plant reflectance increases sharply between red and near-infrared wavelengths, as plants reflect infrared light they cannot use for photosynthesis. This vegetation signature is quite distinctive and might be detectable on exoplanets if vegetation covers substantial portions of the surface. However, alien photosynthetic organisms might not have a red edge. Plants on a planet orbiting a red dwarf star might be black to maximize absorption of the dim red light available, or they might be other colors, entirely depending on their star's spectrum and their photosynthetic pigments. Large-scale color changes across seasons could indicate biological activity. If part of a planet's surface changes color seasonally, perhaps from green to brown, as vegetation grows, and then senesces, this would be difficult to explain through geology alone. Detecting such changes would require extremely high-resolution observations across multiple seasons, pushing the limits of even the most advanced telescopes. But future extremely large telescopes might achieve this capability for the nearest exoplanets. Ocean glint patterns might reveal biological activity in oceans. Certain types of marine life produce compounds that affect water's surface tension or create surface films that change how light reflects off the ocean. These effects, though subtle, create characteristic glint patterns that differ from pure water. Detecting such patterns from light years away would be extraordinarily challenging, but might become possible with next-generation direct imaging telescopes. Atmospheric hazes created by biological activity represent another potential signature. On Earth, isoprene and other organic compounds released by plants contribute to atmospheric haze. On Titan, Saturn's moon, photochemistry creates organic hazes that give the atmosphere its orange color. Distinguishing biological from non-biological hazes would be difficult, but characteristic compositions or variations might provide clues. A planet with organic hazes that change seasonally, for instance, might have biological sources for those hazes. Artificial light on the night side of a planet would be an unambiguous technosignature, a sign not just of life, but of technological civilization. Earth's night side is bright with city lights, electricity use, and various artificial illumination. An alien civilization would likely develop artificial lighting at some stage of technological development, and if they use inefficient lighting that wastes energy by sending light upward into space, rather than directing it all downward toward the ground, their cities might be detectable. However, detecting such faint light from an exoplanet would require extraordinary capabilities beyond current technology, though future direct imaging telescopes might achieve this for the nearest, potentially inhabited worlds. Industrial pollution offers another technological biosignature. Chlorofluorocarbons, CFCs, are entirely artificial. They don't exist naturally and are produced only through industrial chemistry. Detecting CFCs in an exoplanet's atmosphere would be definitive evidence of technological civilization. Other industrial pollutants, nitrogen dioxide from combustion, sulfur dioxide from industry, certain combinations of gases that indicate smelting or chemical manufacturing, might also be detectable. However, some of these gases also have natural sources from volcanoes or other geological processes, so detecting them in amounts far exceeding natural production rates would be necessary to infer industrial activity. The challenge of false positives, non-biological processes that mimic biosignatures, looms large in biosignature detection. every proposed biosignature has at least some possible abiotic production mechanism. Oxygen can come from water photodissociation, methane can come from geology, phosphine might be produced by unknown atmospheric chemistry. Distinguishing true biosignatures from false positives requires careful analysis of gas abundances, combinations, variations over time, and compatibility with the planet's other known properties. Context matters enormously. Finding oxygen in the atmosphere of a planet with a surface temperature of 500 degrees would not suggest life. The planet is too hot for liquid water and likely for any chemistry we would recognize as living. Finding oxygen on a planet in the habitable zone with liquid water on its surface would be far more compelling. Finding oxygen along with methane, nitrous oxide, and seasonal variations in atmospheric composition on such a planet would be extraordinarily difficult to explain without biology. The search for biosignatures requires sophisticated instruments that can analyze light passing through exoplanet atmospheres during transit. As a planet passes in front of its star, some starlight passes through the planet's atmosphere, and gases in that atmosphere absorb light at specific wavelengths, creating an absorption spectrum. By comparing the star's spectrum with and without the planet in front of it, astronomers can determine which wavelengths are absorbed and thus which gases are present in the atmosphere. The James Webb Space Telescope, launched in 2021, has the sensitivity to detect biosignature gases in the atmospheres of certain types of exoplanets, particularly those orbiting small dim red dwarf stars, where the ratio of planet atmosphere to star is more favourable. Future missions propose space telescopes like the Habitable Worlds Observatory or ground-based extremely large telescopes currently under construction will have even greater capabilities, potentially able to characterize Earth-sized planets in the habitable zones of Sun-like stars, the most promising targets for finding life as we know it. These missions might detect multiple biosignature gases simultaneously, observe seasonal and diurnal variations, and potentially even directly image planets and analyze their surface properties. The biosignatures that reveal living planets encompass atmospheric gases that shouldn't coexist, chemical disequilibrium maintained by constant biological production, temporal variations that reflect biological cycles, surface properties that change with seasons, and for technological life, pollution, artificial lighting, and deliberate signals broadcast into space. Each signature provides a puzzle piece, and no single piece definitively proves life. But multiple signatures detected together, in combinations difficult to explain through non-biological processes, could provide compelling evidence that we've detected life beyond Earth, transforming the ancient question of whether we're alone from philosophy into science, revealing that the universe contains not just planets and stars, but living worlds where chemistry has crossed the threshold into biology, where organisms grow and reproduce and evolve, where perhaps intelligence has emerged to contemplate its own existence and wonder, as we do, whether anyone else is out there among the countless worlds orbiting distant stars. The different types of habitable planets. When astronomers speak of habitable planets, they often mean worlds similar to Earth, rocky planets with liquid water on their surfaces, orbiting at comfortable distances from sun-like stars. But the discovery of thousands of exoplanets over the past few decades has revealed that planetary systems come in astonishing variety, with planet types that don't exist in our solar system and orbital configurations that defy early expectations. This diversity suggests that habitability, the capacity to support life, might extend far beyond Earth-like worlds to encompass planet types that seem alien at first glance, yet might provide suitable conditions for life to emerge and thrive. Understanding the different types of habitable planets means expanding our definition of habitability beyond the familiar, to consider the full range of worlds where biology might find a foothold. Ocean worlds represent perhaps the most common type of potentially habitable planet. These are planets covered entirely or nearly entirely by deep oceans, with no dry land or only minimal landmass protruding above water. Earth itself is an ocean world to some degree, with about 70% of its surface covered by water, but true ocean worlds might have water covering 95 or even 100% of the surface, with global oceans potentially hundreds of kilometers deep. Such worlds might form beyond the snowline in their stellar systems, where water ice is abundant during formation, then migrate inward to warmer regions where the ice melts, creating global oceans. Life on ocean worlds might never develop terrestrial forms. Everything would evolve in water, from microscopic plankton to potentially large swimming organisms analogous to whales. Without land, there would be no forests, no land animals, no terrestrial plants. But aquatic life could still be extraordinarily diverse and complex. The key question for ocean worlds is whether photosynthetic life could evolve. Sunlight penetrates only the upper layers of water, so photosynthesis would be restricted to the surface zone. Below a certain depth, life would depend on organic matter sinking from above, or on chemical energy from hydrothermal vents on the ocean floor, much like deep-sea ecosystems on Earth. Extremely deep oceans present another challenge: high-pressure ice. At depths exceeding several hundred kilometers, pressure can become so intense that water freezes despite high temperatures, forming exotic ice structures called Ice 6, Ice 7, and other high-pressure phases that are denser than liquid water. A planet with oceans deep enough to reach these pressures would have a layer of exotic ice separating the liquid ocean from the rocky mantle below. This ice layer would prevent direct contact between water and rock, potentially limiting the availability of minerals and nutrients dissolved from rock that life might need. However, the ice itself might crack due to tidal forces or internal heat, allowing some exchange between the rocky interior and the ocean. Desert planets represent the opposite extreme, worlds where water is scarce, with most of the surface covered by deserts, sand dunes, or bare rock. These planets orbit closer to the inner edge of the habitable zone, where temperatures are higher and water is more likely to evaporate. Any water present might be concentrated in polar ice caps, in subsurface aquifers, or in rare oases where geological features trap moisture. Mars represents a partial example, a cold desert world where water exists mostly as ice, or locked in minerals, with liquid water appearing only occasionally in specific locations. Life on desert planets would need extreme water conservation strategies. Organisms might be active only during rare rain events, spending most of their time dormant. They might extract water from humidity in the air or from chemical reactions rather than drinking liquid water. They might have impermeable skins to prevent water loss, and highly efficient kidneys or equivalent organs that recycle water internally. Plant analogues might photosynthesize only at night when temperatures drop and humidity rises, closing all pores during the day to prevent water loss. Despite the harsh conditions, life could potentially thrive in sheltered microenvironments, shaded canyons, caves where humidity condenses, or underground where water from ancient aquifers remains accessible. Eyeball planets emerge around red dwarf stars when planets become tidally locked, always showing the same face to their star, with one hemisphere in permanent daylight and the other in eternal darkness. The day side receives constant intense heating, potentially creating a hot desert. The night side, receiving no sunlight, freezes solid. But at the terminator, the boundary between day and night, a ring of habitable conditions might exist where temperatures remain moderate. This ring might harbour a circular ocean, the eyeball, surrounded by ice on one side and desert on the other, creating a narrow band where life could flourish. Life on eyeball planets would be restricted to this habitable ring, adapted to conditions that never change. No day-night cycle, no seasons, just constant twilight with the star permanently fixed at the horizon. Organisms might spread around the entire circumference of the planet along this habitable band, but they couldn't expand toward either pole. Moving toward the substellar point would lead to lethal heat. Moving toward the antistellar point would lead to frozen darkness. The planet's climate would feature constant winds as air heated on the day side rises and flows toward the cold night side, creating atmospheric circulation patterns completely unlike Earth's weather. Super-Earths, rocky planets more massive than Earth, but less massive than Neptune, might be the most common type of habitable planet in the galaxy, despite having no analogue in our solar system. These worlds, with masses ranging from about 2 to 10 times Earth's mass, would have stronger surface gravity than Earth. An organism on a super-Earth twice Earth's mass might weigh twice what it would on Earth, creating challenges for movement and structural support, but super-Earths have potential advantages for habitability. Their stronger gravity can hold thicker atmospheres more effectively, providing better greenhouse warming and allowing habitable zones to extend farther from their stars. They might have more active plate tectonics due to greater internal heat, helping regulate climate over geological time. Life on super-Earths would likely evolve shorter, stockier body plans to cope with high gravity. Trees might be shorter and thicker. Animals might have more legs or stronger, thicker legs to support their weight. Flight might be more difficult, requiring more powerful wings and muscles. But the thicker atmosphere might actually make flight easier by providing more air resistance, potentially allowing organisms to evolve gliding or flying capabilities using less energy than on Earth, despite the higher gravity. Mini-Neptunes, planets with substantial hydrogen-helium atmospheres surrounding rocky or icy cores, represent a planet type between rocky super-Earths and gas giants. These worlds might not be habitable at their cloud tops where temperatures and pressures are moderate, but atmospheres are thick hydrogen-helium mixtures. However, some mini-Neptunes might have layers within their atmospheres where temperature and pressure allow water vapor to condense into liquid water droplets, creating water clouds and potentially habitable conditions within the atmosphere itself. Aerial life in these water clouds, floating organisms that never touch solid ground because there is no solid ground accessible, might evolve. Such organisms would need to regulate their buoyancy, perhaps using gas-filled bladders similar to fish swim bladders. They might extract nutrients from atmospheric chemistry or from particles suspended in the atmosphere. Reproduction might involve releasing spores or offspring that drift through the atmosphere until they find suitable conditions to grow. The entire biosphere would be three-dimensional and airborne, with no connection to any surface. Hycean worlds, a term combining hydrogen and ocean, represent a recently proposed planet type that might be surprisingly common and habitable. These are large planets with hydrogen-rich atmospheres and liquid water oceans beneath them, potentially including some mini-Neptunes if conditions are right. The thick hydrogen atmospheres would create greenhouse warming that keeps water liquid even at large distances from the star. Life on Hycean worlds would live in the oceans beneath kilometers of hydrogen atmosphere, never exposed to space but potentially able to thrive in the dark, high-pressure water below. The discovery of biosignatures on Hycean worlds might be easier than on Earth-like planets because their larger sizes and extended atmospheres make spectroscopic analysis more favourable. If life produces gases that reach the hydrogen atmosphere, methane, dimethyl sulfide, or other organic compounds, these might be detectable even with current telescope technology. Hycean worlds thus represent prime targets for near-term biosignature searches. Carbon planets might form in regions of protoplanetary disks, where carbon is more abundant relative to oxygen than in our solar system. Instead of being dominated by silicate minerals like Earth, these worlds might have surfaces and interiors rich in graphite, diamond, silicon carbide, and other carbon compounds. The chemistry of such worlds would be radically different from Earth's. Oceans might consist of hydrocarbons, liquid methane, ethane, or more complex carbon compounds, rather than water. Life on carbon planets, if it evolved, would necessarily use chemistry adapted to carbon-rich, oxygen-poor conditions, potentially resembling the hydrocarbon-based biochemistry speculated for Titan. Lava worlds orbit so close to their stars that surface temperatures exceed the melting points of rock. These planets have surfaces of molten lava with atmospheres of vaporized rock, silicate gases that condense into mineral clouds and rain molten droplets. No life as we imagine it could survive on these surfaces, but some scientists speculate about exotic life existing in the upper atmosphere, where temperatures are lower, or about subsurface oceans trapped beneath the molten surface, where water remains liquid despite the hellish conditions above. Ice worlds covered by thick shells of water ice might be habitable not on their surfaces, which are frozen solid, but in subsurface oceans kept liquid by tidal heating from their parent planet's gravity. Jupiter's moon, Europa, and Saturn's moon, Enceladus, represent examples in our own solar system. Such worlds might be common around giant planets throughout the galaxy. The ice shell provides protection from radiation and impact, while the liquid ocean beneath could harbour extensive ecosystems based on chemical energy from hydrothermal vents rather than sunlight. These worlds would have dark biospheres, no photosynthesis, no dependence on their star, just chemosynthetic life, thriving in hidden seas. Rogue planets drifting through interstellar space with no star at all might still be habitable if they're massive enough to retain thick atmospheres that provide greenhouse warming through atmospheric pressure alone. A rogue Earth-mass planet with a very thick hydrogen atmosphere might maintain liquid water on its surface, despite receiving no starlight, heated only by residual internal radioactive decay and gravitational contraction. Life on such a world would exist in perpetual darkness, depending entirely on chemical energy and internal heat, completely independent of any star. A truly alien biosphere that could drift for billions of years through the void between stars. Binary planet systems where two similarly sized worlds orbit their common center of mass, like Pluto and Charon but potentially both habitable, might create unique conditions. Tidal forces between the planets would generate internal heating. The planets would raise tides on each other. If both have atmospheres, atmospheric circulation might be affected by the nearby companion. Life might evolve on both worlds simultaneously, potentially following different evolutionary paths, or life might spread from one to the other via meteorite impacts that eject material-carrying microorganisms between the two worlds. Trojan planets sharing the same orbit around a star, positioned at stable Lagrange, points 60 degrees ahead of or behind each other, might exist in some systems. These planets would orbit at the same distance from their star, but would see each other as bright points in the sky, visible like particularly bright stars. If both are habitable, civilizations might arise on both, potentially detecting each other's presence long before achieving space travel, since the neighbouring world would be so prominent in their sky. The different types of habitable planets extend far beyond Earth analogues to encompass ocean worlds with global seas, desert planets with scarce water, tidally locked eyeball planets with habitable rings, massive super-Earths with strong gravity, aerial biospheres in thick atmospheres, subsurface oceans beneath ice shells, hydrocarbon-based chemistry on carbon planets, and rogue worlds wandering starless through the galaxy, each type presenting unique challenges and opportunities for life, each potentially harbouring biospheres as rich and complex as Earth's, despite being profoundly different in their physical conditions, demonstrating that the cosmos might contain not just one type of living world, but a vast diversity of habitable environments where chemistry, energy, and time have combined to create the extraordinary phenomenon we call life, scattered across countless worlds in forms we're only beginning to imagine. The invisible forces holding galaxies together. When you look at a photograph of a spiral galaxy, you see a beautiful pinwheel of stars, gas, and dust rotating around a central bulge. The image suggests a structure held together by visible matter, the billions of stars whose light creates the galaxy's luminous form. But appearances are deceiving. The forces actually holding galaxies together are largely invisible, operating through mechanisms both understood and mysterious. Gravity binds these cosmic structures, but most of the mass providing that gravity cannot be seen, cannot be detected except through its gravitational effects, and remains one of the deepest mysteries in astrophysics. The first clue that something invisible was holding galaxies together came from studying how stars move within them. In the 1970s, astronomer Vera Rubin conducted detailed observations of spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic centers. According to Newton's laws of motion and gravity, objects farther from the center of mass should orbit more slowly, just as Neptune orbits the Sun much more slowly than Mercury. The visible matter in galaxies is concentrated toward the center, with the brightness falling off dramatically in the outer regions. Based on this distribution of visible matter, stars in the outer parts of galaxies should be moving much slower than stars near the center. But that's not what Rubin found. Instead, the rotation curves, graphs showing orbital velocity versus distance from the center, were flat. Stars in the outer regions were moving just as fast as stars closer to the center, sometimes even faster. This could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars, gas, and dust. This additional mass had to extend well beyond the visible disk, forming a massive spherical halo surrounding each galaxy. The nature of this dark matter remains unknown, but its gravitational effects are undeniable. Galaxies are embedded within dark matter halos that contain several times more mass than all the visible matter combined. A typical spiral galaxy, like the Milky Way, might contain about 100 billion solar masses of visible matter, stars, gas, dust, planets, but resides within a dark matter halo containing perhaps 1 trillion solar masses. This dark matter halo extends perhaps 10 times farther than the visible disk, creating a gravitational well that holds the galaxy together. Dark matter doesn't interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any wavelength. It interacts with normal matter almost exclusively through gravity. This makes it invisible to telescopes, but reveals its presence through gravitational effects. The flat rotation curves that Rubin observed were the first clear evidence, but dark matter reveals itself in other ways as well. Gravitational lensing provides some of the most compelling evidence for dark matter in and around galaxies. According to Einstein's general theory of relativity, mass warps spacetime, and light follows the curves in that warped geometry. When light from a distant galaxy passes near a massive object, its path bends. By measuring this bending and calculating how much mass would be needed to produce it, astronomers can map the distribution of mass, including dark matter. These mass maps show that dark matter is distributed in huge halos around galaxies, exactly as predicted from rotation curve studies. The bullet cluster provides particularly dramatic evidence. This structure formed when two galaxy clusters collided and passed through each other. During the collision, the hot gas from each cluster, normal matter that can interact with itself, slowed down and remained near the collision site, heated by the impact. But gravitational lensing maps show that most of the mass is not where the gas is. Instead, it separated from the gas and continued moving with the galaxies themselves. This separated mass must be dark matter, which doesn't collide or interact with normal matter except through gravity, passing right through during the cluster collision. The gravitational force from dark matter operates according to Newton's law of universal gravitation for most purposes, though general relativity provides the more accurate description, especially in strong gravitational fields. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Even though individual dark matter particles don't clump together the way atoms do, they can't radiate energy and settle into compact structures. Collectively, they form halos through gravitational attraction, with each particle orbiting in the combined gravitational field of all the others. These dark matter halos formed before the visible galaxies themselves. In the early universe, dark matter could begin collapsing into clumps earlier than normal matter, because dark matter doesn't interact with radiation. Normal matter, coupled to photons in the early universe, couldn't collapse efficiently until after recombination, when electrons combined with nuclei to form neutral atoms, and the universe became transparent. By that time, dark matter had already created gravitational wells, regions of enhanced density, and normal matter fell into these wells, forming the first galaxies within the scaffolding of dark matter structure. Computer simulations of galaxy formation must include dark matter to reproduce the observed properties of galaxies. Simulations using only normal matter produce galaxies that look nothing like what we observe. But when dark matter is included, with properties consistent with observations, non-interacting except through gravity, with a specific abundance relative to normal matter, the simulations produce galaxies remarkably similar to real ones, with flat rotation curves, realistic sizes, and appropriate clustering properties. The dark matter distribution within galaxies follows a characteristic profile. The density is highest at the center and decreases toward the outer regions, but much more gradually than the distribution of visible matter. Various mathematical models describe this distribution, with names like the NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who studied dark matter halos in simulations in the 1990s. These profiles predict specific density distributions that can be tested against observations through rotation curves and gravitational lensing. But dark matter isn't the only force holding galaxies together. Gravity from visible matter contributes as well, though less than dark matter. The combined gravitational pull from billions of stars, gas clouds, dust, and the supermassive black hole at the center all help bind the galaxy. The distribution of this visible matter creates the gravitational potential in which stars orbit, and while dark matter dominates the total mass, the visible matter shapes the inner regions where most stars reside. Orbital mechanics plays a crucial role in keeping galaxies stable. Each star orbits in the combined gravitational field of all other matter in the galaxy, both visible and dark. Stars don't simply circle the galactic center in perfect circles like planets orbiting the Sun. Their orbits are more complex, elliptical, and tilted at various angles, creating the three-dimensional structure of the galaxy. In spiral galaxies, the disk forms because stars that were born from a rotating cloud of gas inherited that rotation, and collisions between gas particles dissipated energy and flattened the distribution into a disk. The supermassive black hole at the center of most galaxies contributes to holding the inner regions together, though its mass is typically small compared to the total galaxy mass, perhaps 0.1 to 1% of the bulge mass. The black hole at the center of the Milky Way, Sagittarius A star, contains about 4 million solar masses. While this is enormous by any terrestrial standard, it's tiny compared to the Milky Way's total mass of perhaps 1 trillion solar masses, including dark matter. The black hole's gravitational influence dominates only in the innermost few light years. Spiral density waves also play a role in galactic structure, though they're not forces holding the galaxy together in the same sense as gravity. These waves are regions of enhanced density that rotate through the disk, compressing gas and triggering star formation. The spiral arms we see are not fixed structures, with the same stars always in them, but rather patterns that rotate at a different speed than the stars themselves. Stars move in and out of the spiral arms as they orbit, spending more time in the arms where the density is higher, creating the appearance of persistent spiral structure. Galaxy clusters add another layer of complexity. Galaxies themselves are held together primarily by their dark matter halos, but galaxies cluster together in groups and clusters, which are themselves held together by even larger dark matter halos. The Milky Way is part of the Local Group, which includes the Andromeda Galaxy and about 50 smaller galaxies, all orbiting within a common dark matter halo. Galaxy clusters, like the Virgo cluster, contain thousands of galaxies within a massive dark matter halo containing quadrillions of solar masses. The dynamical state of galaxies, whether they're stable, expanding, or contracting, depends on the balance between kinetic and potential energy. If the kinetic energy of all the stars and gas exceeds twice the magnitude of the gravitational potential energy, the galaxy would be unbound and would eventually fly apart. The fact that galaxies remain bound over billions of years tells us that they're in virial equilibrium, a state where kinetic and potential energy are balanced according to the virial theorem. This relationship allows astronomers to estimate the total mass of galaxies from observations of how fast their contents are moving. Some alternative theories propose that dark matter doesn't exist, and that instead, our understanding of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. MOND can reproduce flat rotation curves without dark matter, but it struggles to explain other observations like gravitational lensing and the bullet cluster. Most physicists consider dark matter more likely to be a new type of particle rather than a modification of gravity, though the question remains open until dark matter is directly detected or conclusively ruled out. The search for dark matter particles continues in laboratories around the world. Experiments deep underground attempt to detect rare interactions between dark matter particles and normal matter. Other experiments search for signals of dark matter particles annihilating with each other or decaying into detectable particles. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. So far, no experiment has definitively detected dark matter particles, but each null result constrains the possible properties of dark matter, narrowing the possibilities. The invisible forces holding galaxies together operate on timescales of hundreds of millions to billions of years. A star near the Sun's position in the Milky Way takes about 225 million years to complete one orbit around the galactic center. During this time, the combined gravitational pull from the dark matter halo, the visible matter in the disk and bulge, and all other components keeps the star bound to the galaxy. The stability of this configuration over billions of years, galaxies don't fly apart, they maintain their structures over cosmic time, testifies to the power and precision of the gravitational forces at work. Understanding the invisible forces holding galaxies together remains one of the central challenges in astrophysics. The existence of dark matter is now accepted by most scientists based on the overwhelming gravitational evidence, but its fundamental nature remains mysterious. Whether it consists of weakly interacting massive particles, axions, primordial black holes, or something entirely unexpected, dark matter's gravitational pull provides the invisible glue that holds galaxies together, shapes their structure, determines their evolution, and creates the cosmic web of large-scale structure that defines the universe on the largest scales. making dark matter's invisibility one of the most tantalizing mysteries in science, a substance that makes up most of the universe's mass, but reveals itself only through the ancient and universal force of gravity that governs the motion of everything, from falling apples to orbiting galaxies. The afterglow of the Big Bang. Throughout the entire universe, in every direction you could possibly look, there exists a faint glow of microwave radiation that fills all of space. This radiation isn't coming from stars or galaxies or any object in particular. It's coming from everywhere at once, a ghostly remnant from the earliest moments of cosmic history. This is the cosmic microwave background, the oldest light in the universe, and it carries within it a snapshot of what the cosmos looked like when it was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. To understand this afterglow, picture the universe in its earliest moments. At the very beginning, everything that exists now, all the matter and energy in hundreds of billions of galaxies, was compressed into an infinitesimally small point. The Big Bang wasn't an explosion in space, but rather an expansion of space itself. In those first fractions of a second, the universe was unimaginably hot and dense, so hot that matter as we know it couldn't exist. There were no atoms, no nuclei, not even stable protons or neutrons. There was only a seething soup of fundamental particles and energy, all in thermal equilibrium at temperatures of trillions upon trillions of degrees. As the universe expanded, it cooled, following a fundamental principle of thermodynamics. Think of how a spray can get cold when you release the compressed gas inside. Expansion causes cooling. The universe cooled rapidly in those early moments, dropping from inconceivable temperatures down to merely billions of degrees within the first few minutes. At this point, conditions became cool enough for protons and neutrons to stick together, forming the nuclei of the lightest elements, primarily hydrogen, some helium, and trace amounts of lithium and beryllium. This period, called Big Bang nucleosynthesis, lasted only about 17 minutes, but it determined the basic chemical composition of the universe for hundreds of millions of years to come. But even after nuclei formed, the universe was still far too hot for atoms to exist. Free electrons zipped through space at tremendous velocities, and any time they got near a nucleus, the ambient heat would knock them away before they could settle into orbit. The universe was filled with a plasma, a mixture of atomic nuclei and free electrons, and this plasma was opaque to light. Photons couldn't travel far before colliding with a free electron and scattering in a new direction. Light was trapped, bouncing endlessly between particles in a cosmic fog that filled all of space. For the next 380,000 years, the universe continued expanding and cooling, but it remained opaque. The temperature dropped gradually from millions of degrees down to thousands of degrees. Then at around 3,000 degrees Kelvin, still hot enough to melt any metal, something remarkable happened. The universe had finally cooled enough for electrons to combine with nuclei and form stable atoms. This moment is called recombination, though that's actually a misnomer since the electrons and nuclei were combining for the first time, not recombining. When recombination occurred, the nature of the universe changed fundamentally. With electrons now bound into atoms, there were suddenly far fewer free charged particles for photons to scatter off of. The cosmic fog cleared almost instantaneously on cosmic timescales. Light that had been trapped, scattering endlessly through the plasma, was suddenly free to travel unimpeded through space. The universe became transparent. The photons that were released at that moment of recombination have been travelling through space ever since. They filled the entire universe then, and they fill the entire universe now. These photons form the cosmic microwave background. They are the afterglow of the Big Bang, the first light that could freely travel through the cosmos. But here's the crucial part. Those photons have been stretched by the expansion of the universe. When they were released 13.8 billion years ago, they were primarily visible light and infrared radiation, corresponding to the 3000-degree temperature of the universe at recombination. But as space itself expanded, the wavelengths of these photons were stretched along with it. Light that was once visible orange has been stretched into infrared, then into far infrared, and finally into microwave radiation. The cosmic microwave background today corresponds to a temperature of just 2.7 degrees above absolute zero, 2.7 Kelvin. This stretching of light by the expansion of space is called cosmological redshift, and it's one of the most direct pieces of evidence for the Big Bang theory. The universe has expanded by a factor of about 1,100 since recombination, and the wavelength of the cosmic microwave background radiation has been stretched by exactly this same factor. What was once a hot glow of visible light has become a cold bath of microwave radiation. The cosmic microwave background is incredibly uniform. No matter which direction you look in the sky, the temperature is almost exactly the same, 2.725 Kelvin, with variations of only about 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous. There were no large structures, no concentrations of matter, just an almost perfectly uniform distribution of hydrogen and helium gas filling all of space. But those tiny variations, those fluctuations of 1 part in 100,000, are extraordinarily important. They represent slight differences in density and temperature in the primordial plasma. Some regions were slightly denser and hotter, others slightly less dense and cooler. These fluctuations were the seeds of all structure in the universe today. The denser regions had slightly stronger gravity, which allowed them to attract more matter over time. Over hundreds of millions of years, these tiny density differences grew, eventually collapsing to form the first stars, then galaxies, then galaxy clusters, and ultimately the entire cosmic web of structure we see today. When astronomers map the cosmic microwave background in detail, they're seeing a snapshot of these primordial fluctuations. Sophisticated satellites, equipped with incredibly sensitive detectors, measure the temperature of the cosmic microwave background across the entire sky, creating maps that show warmer and cooler spots. These maps look like mottled patterns of slightly different colours, almost like abstract art, but they're actually baby pictures of the universe, showing the distribution of matter when the cosmos was just 380,000 years old. The patterns in the cosmic microwave background aren't random. They have specific statistical properties that depend on the fundamental parameters of the universe. How much normal matter exists, how much dark matter, how much dark energy, the rate of expansion, the curvature of space, and more. By analysing these patterns in exquisite detail, cosmologists can measure these parameters with remarkable precision. The cosmic microwave background has become the single most important tool for determining the basic properties of our universe. One of the most striking features visible in cosmic microwave background maps is the presence of acoustic oscillations, essentially sound waves in the primordial plasma. Before recombination, the plasma was hot and under tremendous pressure from radiation. Regions that were slightly denser had stronger gravity pulling inward, but they also had stronger radiation pressure pushing outward. These competing forces created oscillations, with dense regions compressing and then rebounding, creating waves that propagated through the plasma, much like sound waves travel through air. These acoustic oscillations were frozen into the distribution of matter at the moment of recombination. The characteristic scale of these oscillations, the typical distance between peaks and troughs, shows up as a specific pattern in the cosmic microwave background, radiation background, temperature fluctuations. By measuring this pattern precisely, astronomers can determine how far these sound waves had travelled by the time of recombination, which in turn tells them about the geometry and expansion rate of the universe. The cosmic microwave background also has a subtle property called polarization. Light can be polarized, Its electric field can oscillate in a preferred direction, and the cosmic microwave background photons carry polarization information from the moment they were released. This polarization was created when the photons scattered off electrons for the last time before recombination. The pattern of polarization across the sky carries additional information about conditions in the early universe, including potentially evidence of gravitational waves from the inflationary period that may have occurred in the first tiny fraction of a second after the Big Bang. There are actually two types of polarization patterns in the cosmic microwave background, called E modes and B modes. E modes are relatively easy to detect and have been thoroughly mapped. B modes are much fainter and harder to detect, but they're particularly interesting because primordial gravitational waves would create a specific B mode pattern. Detecting this signal would provide direct evidence for cosmic inflation and would open a window into physics at energy scales far beyond what we can achieve in particle accelerators on Earth. The cosmic microwave background isn't perfectly smooth in its distribution across the sky. There's a slight asymmetry, a dipole pattern, where one side of the sky is slightly hotter and the other slightly cooler. This dipole is caused by the motion of our solar system through space. We're moving at about 370 kilometers per second relative to the cosmic microwave background, carried along by the motion of the Sun around the galaxy, the motion of the galaxy through the local group, and the motion of the local group through the universe. This motion causes the cosmic microwave background to appear slightly blue-shifted, and therefore hotter in the direction we're moving toward, and slightly red-shifted, and cooler in the direction we're moving away from. Once this dipole is removed from the data, along with contamination from our own galaxy's emission, what remains are the primordial fluctuations, the image of the universe as it was 380,000 years after the Big Bang. These fluctuations exist on multiple scales, from features spanning large portions of the sky down to the smallest angular scales that satellites can resolve. Each scale carries different information about the early universe and the physical processes that shaped it. The cosmic microwave background has also been used to test fundamental physics. The spectrum of the radiation, how much energy exists at each wavelength, matches a perfect blackbody spectrum, more precisely than any artificial source humans have ever created. This perfect blackbody spectrum is exactly what's expected from matter and radiation in perfect thermal equilibrium, providing strong confirmation that the early universe was indeed in this state. Photons from the cosmic microwave background pass through everything. Right now, billions of these ancient photons are streaming through your body every second, traveling through space for nearly 14 billion years before encountering the atoms in your cells. They pass through largely without interaction because microwave radiation interacts very weakly with ordinary matter at everyday temperatures. The entire Earth is bathed in this ancient light, as is every planet, every star, every galaxy. It's a universal background that permeates all of existence. The discovery of the cosmic microwave background in 1964 was accidental. Two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna and kept detecting a persistent noise that came from all directions and wouldn't go away no matter what they did. They initially thought it might be interference from nearby New York City, or perhaps noise from the electronics, or even from bird droppings on the antenna. Only when they consulted with theoretical physicists did they realize they had detected the afterglow of the Big Bang, earning them the Nobel Prize. This radiation has been cooling for billions of years and will continue cooling forever. As the universe expands, the cosmic microwave background will be stretched to longer and longer wavelengths, eventually becoming radio waves, then longer wavelengths still. Its temperature will approach closer and closer to absolute zero, but will never quite reach it, always remaining as a faint reminder of the hot, dense state from which our universe emerged, carrying information about cosmic dawn across the vastness of space and time. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance, because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, 2 stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion.